Jenny Early. I'm Director of Business Planning at Taylor & Francis, and this session is about artificial intelligence. I'm very pleased to introduce Sam Herbert and Ruth Pickering, and they're going to demonstrate and describe some real-world applications of AI, and also discuss the pertinence to the world of publishing. Sam is co-founder of 67 Bricks. He started with a first in physics and a passion for technology, ignited by his wonder at the sheer immensity of the universe. Turning down the opportunity to work on nuclear power or missile systems, he cut his teeth on microchip programming for Z80 chips and program management at Cancer Research. He started 67 Bricks 10 years ago, and he's going to show us today how we can realize more value from our content through the use of AI.
Thanks, Jenny. Okay, as Jenny said, my name's Sam Herbert. I'm co-founder of 67 Bricks. Again, as Jenny said, artificial intelligence is generating a lot of interest at the moment. So the organizations like Google, Amazon, Facebook, IBM are all investing huge sums of money into artificial intelligence. And some of the applications that they're developing are starting to come through in the systems that they build and they manage. So there are two clear implications for us in publishing. The first is that your users' expectations are changing. They're starting to interact with systems that are more intelligent. Secondly, there are opportunities for you from artificial intelligence. So I think my role here at the start of two sessions really is to give you an introduction to artificial intelligence, to think a bit about what the impact might be in the future, and then to look a little bit about what we can do about that in publishing. So, very brief introduction to 67 Bricks. We build content platforms for publishers, and we use approaches like machine learning, AI, and natural language processing in the content platforms that we build to help publishers increase automation, develop revenue streams, and deliver more value to content consumers. So let's start with a definition of artificial intelligence. Now, in truth, there isn't really a lot of agreement about a definition of artificial intelligence, but this is the one that we like to work with at the moment. So it's the use of computers to simulate human intelligent behavior to tackle complex problems that are difficult to solve using traditional computational approaches. Okay? But let's break that down a little bit. So we're aiming to simulate human intelligent behavior. That makes sense. But actually one of the things that's been holding artificial intelligence back for a long time is the plan or the intention to actually copy or mimic how our brain works and how humans are intelligent. And actually more recently, the approaches that have worked have actually identified and understood the differences between computers and humans. So humans, huge processing power, but actually very limited ability to hold and store and access large quantities of data. In comparison, computers, not so much processing power, but huge ability to store and access very quickly huge quantities of data. And the approaches that understand those differences are the ones that are starting to really work. Another thing is that we're thinking about really complex problems. Now, what is a complex problem is kind of determined by your point in history, I guess. So if I said, 15 years ago, I'm going to give you a device that you can put in your pocket that's going to give you directions to your local pizza restaurant through potentially 4 different forms of transport in the space of a couple of seconds, you would be pretty amazed. And you'd probably think about that being something like artificial intelligence. But now that we have it, it just seems normal. It's just software now. So typically, artificial intelligence seems to be the thing that's always over the horizon, the thing we haven't quite done yet. And the next bit that's interesting to look at is the comparison to traditional computational approaches. So for the main part, software development has been carried out or been achieved through software developers writing individual rules and then creating libraries of rules and then building on those libraries. But that doesn't really work in an environment where you're thinking about the environments that we're talking about, it's kind of the real world for humans. The number of kind of scenarios we're dealing with there, the number of rules you would need to write there are just far too complex to really solve in that kind of way. So modern artificial intelligence approaches are the ones where you're giving it the data and it's working out the rules, and it's potentially working out large numbers of different rules in an automated way and potentially in a dynamic way as more data is fed into it. And those are the approaches that are really working. So, one of the really interesting questions I think it's hard to answer but is really interesting to look at is what is going to be the impact of artificial intelligence in the future? And I think that's, if we have an understanding of that, as publishers, we can start to make some decisions about what we do now. The model that I found that's most interesting and most useful in doing that is a macroeconomic model. And it looks at what happened in previous technology innovations and then tries to understand what might happen with AI. So this is my one page on a brief history of technology innovation. So we have microchips. We had microchips. Huge impact on many aspects of our lives. But if we think about the macroeconomic impact, we might suggest that would be a reduced cost of arithmetic. That's essentially what microchips gave us. And then we can look at what did that mean? What did it mean to have a reduced cost of a capacity or a capability? And the first thing that we saw, or the first thing that we saw in history was that obviously tasks that involved arithmetic reduced in cost. So, for example, organizations carrying out financial forecasting. Previously, that was a heavily human task, and not all organizations could carry it out. With the advent of reduced cost arithmetic, that was a very easy thing to do and was accessible to all organizations. The second major impact is that complementary tasks increase in value. So once you had organizations, all organizations being able to do financial forecasting, then there was an increase in value in things like tax planning or judgment or analysis, and the value of those services increased. The third major impact was a reframing of tasks. So where previously drug discovery was primarily a chemistry or biology activity, it got reframed as an arithmetic task, a computer-based task. Okay, so let's move on. We have microchips, we have digitization, and potentially you could consider the macroeconomic impact of digitization as a reduced cost of search and communication. The ability to search the internet for the wealth of human knowledge, very, very powerful. But let's move on to AI. So again, it's interesting to think about AI and then look at what happened in history. So I would suggest that one way to think about AI as a macroeconomic impact is a reduced cost of prediction. And that's really interesting because most human behavior involves some element of prediction. So again, looking back in history, what does that mean? What can we infer from history? Well, first of all, we can assume that tasks that involve prediction are going to reduce in cost. The ability to predict whether someone has a particular disease or whether they're going to get a particular disease is going to reduce in cost. And that cost reduction primarily comes about from the removal of humans in a large portion of that activity. And the second impact that we might see is that complementary tasks around the reduced cost of prediction are going to increase in value. So in that scenario, you've suddenly got many, many people all having early warning signs of potential diseases they're going to get in their 20s or their 30s or their 40s. You're suddenly going to need a whole load of more services around treatment of diseases, but maybe more importantly, things like empathy and counselling and ethics. All of those things are going to become far more important when everyone has a clear understanding of all the different diseases they're going to get over their lifetime. Artificial intelligence covers, there are lots of different approaches within artificial intelligence, and I'm not here to talk about them in any technical detail, but the one that's really gathering a lot of interest at the moment and the one that's getting a lot of the investment, and actually it's generating something like 60% of the investment into artificial intelligence is into machine learning. So I thought it interesting to talk a little bit about that and what it is. So a software application can be considered to be using machine learning where its performance in a particular task improves with experience. A couple of things to note there. It's really important to frame the task correctly. And secondly, getting the experience data is really, really interesting and a difficult challenge, and actually a real opportunity for the publishing industry. A lot of these machine learning organizations are going to be looking for data, experience data. You have some really interesting and valuable data. But in terms of trying to talk you through what machine learning is, I'm just going to give you the most basic machine learning demo I can possibly give you. So here we have, the task I've given the computer is to tell me whether these recipes are either meat or vegetarian. That's the task I've given it. And the only information I've given it is the text of the recipe. I've given it no information about a knowledge model, I've given it no taxonomy or ontology or anything like that. So the first, and it's currently guessing that they're all vegetarian. It's just making a random 50-50 guess. It's guessing the vegetarian. So I give it one piece of experience data, and I tell it that beef stew is meat. It now thinks all the rest of them are meat. We haven't got much further yet. But I give it one more piece of experience data, and I tell it that onion soup is vegetarian, and it can correctly identify what the subsequent recipes are, either meat or vegetarian. And it's doing that purely on the rules that it's created for itself, based on the text that it has. Okay, back to the slides. So just going to talk through a couple of examples of machine learning from the wider industry. So there was a test carried out that looked at how good would a machine be at identifying breast cancer. How would it compare to a human doctor? So what they did was they took tens of thousands of scans. They fed that into the machine and told the machine as well whether a particular scan that person had cancer or not. The really hardest bit of this task, I understand, was the bit about turning the image into data that the machine could read, machine-readable data. But once it had done that, they could feed the machine data into the machine learning application, and then it could learn to identify what it saw as the key indicators of breast cancer. And it turns out that it is actually better than a human at identifying breast cancer from a scan, which is exciting. Another example is driverless cars. This area of kind of software started in the world of warehousing. So in the warehouse environment, the machine's driving along without an operator. If there's a box in front of you, stop. Or if there's a box in front of you and there's space for you to go around it, go around it. So you can write some fairly simple rules to drive a robot around a warehouse. When you take that into the real world, massively more complex. Start to think about some of the rules you'd have to write to tell a computer what to do in a situation on a road. Hugely complex. And they didn't make much progress until a machine learning approach was applied. So what they did was they sat drivers in cars, and those cars had multiple sensors. Large number of sensors around the cars, and it was actually tracking what the human was doing, what they were doing. And so the machine then gathered all of that data, and it was millions of hours of driving was captured. And then the machine essentially took all that data and then started to predict what would a human do in this scenario that I'm experiencing right now. And that's where the significant improvement in driverless cars has come about from, and that's why we're now seeing driverless cars on the roads, particularly at this stage in test scenarios, but it's coming. Okay, so the publishing industry. Associated Press carried out a test. They wanted to see whether a machine learning approach could write news, human-readable news items. They had a team of 6 people, humans, journalists, writing news articles about companies. And it was information like, has the yield gone up? Has the board changed? Those kinds of things. And so what they did in the test was they fed all of the news items into the machine. They fed it with the research data that those journalists had used to determine that news article. And then they allowed the machine to come up with its own approach to writing news articles. And it turns out that a machine could create 10 times as many news items as the team of 6 journalists. But what's most interesting, I think, is that it also increased the quality of those news items. What I understand happened at Associated Press was what they did was they took the people and they retasked them. And they asked them to analyse the news items. And they actually started asking them to write thought leadership pieces, to do trend analysis. And so they got the computer doing what you might consider the more grunt work, raised the output from the whole team and raised the value of the output to their customers. Another example is some research that's been done to look at, can you predict the future impact factor of a research article before it's published? And the research suggests that, yes, you can. And there are some applications out there that do this. And what was done there, I understand, was that the machine was fed with all the research articles, the content of all the research articles, and associated metadata about them, and obviously their subsequent impact factor. And what's interesting about a machine learning approach is that it just loves data. So you can imagine being able to add additional data to that. You can add information about the author. You could add information about the research institute they carried that research out in, what previous research they'd carried out, who they were doing the research with. But also, potentially more interestingly, you could start to feed in environmental data, like what's happening in the scientific community. What science news items are getting real interest? And you could feed that into the machine to also power that machine learning approach. So, in our work with our clients, we've built a number of applications that use AI approaches. So we see a lot of potential opportunities for the information industry, for you publishers. But I'm just going to pick on a couple and talk through what happened there. So improving marketing communications. What you can do there is you can essentially analyze journal articles, create what we call a semantic fingerprint for those journal articles. You can then, you have information about your users or your organizations, about which content they have accessed. You can then infer a semantic fingerprint for those users or institutions. So they then have a semantic fingerprint. And as a new piece of content comes in, you create a semantic fingerprint for it, you compare it with the organization's semantic fingerprint, and you make matches, and you say, this is something that we know that organization is going to be really, really interested in, or that user is going to be really, really interested in. And you start to feed that in through your marketing communications. And the response rates we've seen increase. Another opportunity is around identifying peer reviewers. A similar approach you create a semantic fingerprint for journal articles, you infer a semantic fingerprint for authors based on the semantic fingerprint of the research articles that they have written. And then as a new article comes in, you want a peer reviewer for it, you compare the semantic fingerprint for that article with the semantic fingerprint of all your authors, and you have a match. You can identify and you can provide and you can identify weighting as well, and you can identify the top 10 most likely, most relevant reviewers for that particular piece of content. So that's my brief introduction to artificial intelligence. Hopefully it's been useful. It's a subject, and if you've talked to me about it already, you know this, but it's a subject I have a huge passion for. So if you're interested in having a conversation, I'd really love to have a conversation with you. Please ask me some more questions. So, thank you.
Hi. It's a bit of a basic question, really.
Good.
But when you're talking about artificial intelligence, how much data do you need to supply to the software to enable it to actually work properly?
So the demo that I gave you needs very, very little data because, is this on? Because the challenge, the task we're trying to carry out is incredibly simple. So essentially the amount of data that you need increases as the complexity of the task you're trying to carry out. We talked a little bit about driverless cars. The amount of data that they need to feed into the machine is huge. Millions of hours of driver data and environmental data coming from multiple sensors around the car. So it really depends on the problem that you're trying to solve.
Thanks very much. So what I'd like to do is to take you back to 2009, where our story really starts. So in 2009, the current CEO of Yewno was studying applied mathematics at King's College London, and he was specifically focused on the field of econophysics. So econophysics is a discipline that aims at explaining economic and financial cycles using structured mathematics derived from physics. And he was working with the financial community in London, looking at unstructured texts and creating predictive analytics. And when that was successful, he wanted to move into a different domain of information. So again, complex systems, this time focused in life sciences. So he started looking at if he could ingest high volumes of unstructured text, this time medical documents, scientific documents, and to try and identify cures for rare diseases. So he ingested 23 million PubMed records and created a proof of concept that was very successful. And this was when he met Mike Keller, who's the vice provost and librarian at Stanford. And when Mike saw the technology and what had been achieved in the life sciences domain and in the financial domain, he said to him, I don't think this technology is life science specific. I think it could be applied to an interdisciplinary set of information. And he invited him to move to Stanford to finish his PhD and to build an interdisciplinary research tool for the Stanford Libraries. And that's the very beginning of Yewno. So in 2014, one of the first projects we started when we created Yewno was working alongside the Stanford Libraries. We had 10 million documents. We had 5 million items that Stanford gave us that were full text items, books, journals, across a range of disciplines. We took the whole of Wikipedia. And we were aiming to create this proof of concept to see if you can indeed create an interdisciplinary research environment. The project was called HARRY. HARRY stood for the Hyper Association of Related Inferences. So what we have here is in fact an inference engine. So our version of AI is a huge field. It's like saying science or medicine. So we focus specifically on computational semantics, graph theory, and machine learning. So what I'm going to show you today is the current application that's in use at Stanford and many other places. And we have about 125 million items now ingested. And this provides a very different type of search. So it's conceptual search. So the way our technology works is that we read the full text of all documents. So we receive the full text and metadata from publishers, and we also use open access sources, but we don't use the metadata for our research results. We use them to point the content back to the publisher. But our algorithms are reading the full text. And from that, they're identifying meaning in the form of concepts, and then they're knitting it together into an enormous graph network. And what we're trying to do with our use of artificial intelligence is to recreate a neural network model. So we're trying to create a way of a computer thinking in the way that a human brain would think if it could read 125 million books, journal articles, and other sources. So I'm going to take you here to the homepage of Stanford Libraries, and I'm going to start typing. So I'm not asking you at this point to choose what search box to go to, what platform to go to, what database, etc. I'm just putting a query into the main database, and I'm going to see what happens. So what you get next is the website, and I'm offered books and media. I'm offered the library website, databases, articles, and e-resources. And here I'm offered concepts and connections, and this is the Yewno product. So if you go to a lecture and your professor says, read this article or read this book, and you put that into a search bar, you'll get a brilliant answer in probably under a minute. But if you go to a lecture and someone says to you, explore the Fairy Queen, and you don't know when it was written, who wrote it, what was happening historically at the time, anything about the political context, you may not know where to start your search. And in fact, that was the case when I was working with an English literature professor at a very well-funded research institution. She was teaching this class on the Fairy Queen to a group of 18 and 19-year-old students who are mostly computer science majors. And she said they can't find anything because they don't know what to look for. So starting this search, what you see on the left-hand side is what we call the information panel. So immediately you get here an overview, which is a definition of what you search for. So I was looking for the Fairy Queen, and here it tells me the Fairy Queen is one of the great long poems in the English language written in the 16th century by Edmund Spenser. Next, it gives me a list of all of the concepts related to my search. So I can scroll down here, and I get all of these items along with a definition, so I can understand the context of what was happening. And if I'm interested immediately to go into documents, I can get into this panel and I can scroll down and see a series of documents. And anything I'm interested to read, I can click into and it will bring me up a snippet of information. Now, the important thing about this snippet of information is that this isn't the first page or the abstract or the first chapter of the book. This is very specifically the part of the text where that concept was found. So you're taking the person right to the relevant element of that document. And the reason we give people these quite long snippets is that 2 years ago, before we launched the first proof of concept, we did a lot of research. And what people said was most frustrating about their searches was when they found something and they thought it was what they were looking for because they'd read a couple of lines and they clicked through and it wasn't what they were after. So what we're trying to do here is to give people enough information so that if they do choose to click to the full text, they're actually not disappointed with the result. But the most important part of the product is on the right. It's the graph. So I mentioned that we use computational semantics, machine learning, and graph theory. And a graph is a hugely flexible mathematical instrument. So what you have here on the right is the concept that I was searching for, the Fairy Queen, surrounded by all of these related concepts. And as I hover my cursor over each of the items, I'm showing you the secondary connections. So everything I'm showing you in the graph is obviously connected to the Fairy Queen, which was my first search. But as I move around, many of the other items are also connected. And the important thing about this is that anything you see is interactive and clickable. So if you're interested in understanding any of the other concepts, or equally any of the other concept connections, you can click on either the concept node itself or a line to understand what that's all about. So we can move around, and you can see each of these things will light up as I hover over it. Maybe I'm interested to understand the connection between Elizabeth I. So I'm going to click on that concept node. And so what appears now in the left-hand panel is an overview, again, a definition of Elizabeth I of England. Again, I'm going to have concepts all related to Elizabeth I, and then I'm going to be straight into a highly relevant document list. And if I decide that Elizabeth I is the angle that I'd like to pursue in my research, I can click here on this expand concept button, and Elizabeth will be added into the graph. So this is really showing you what the product's all about. So I mentioned at the beginning, it's an inference engine. It's designed to find connections, relationships, and infer in the same way that the human brain would. So what you have at the top is your first search, the Fairy Queen. Then we have Elizabeth I of England that I added. Then all of these items in the middle are the things that connect those two. So we can scroll across and see what they are. Charles Howard, Robert Dudley, Francis Walsingham. And when you find something you're interested in, so Francis Walsingham, name doesn't ring a bell to me, so I'm going to click on that and understand who he was. So Francis Walsingham was an English statesman and diplomat, Secretary of State in the reign of Queen Elizabeth. So that explains why he's connected. And if I decide I want to add him, again, I just click on Expand Concept, and Francis Walsingham will be added into my chart, and I'll see all of the connections between him, the Fairy Queen, Elizabeth I. And so you can see this graph, this visualization growing in front of your eyes. And we see three main uses for it. The first is just really around learning and understanding. At a single click, when you open a graph, you get the context, you get the concepts that surround your main query, and you're able to understand the context that is relevant and the other things that are relevant to your search. The second thing is really about connections and inferences, to understand the relationships between two items. And the third use is all around serendipity. So there's everything you know that you don't know that you can search for in a search bar, and there's what you don't even know to look for in the first place. And what we find when people use the product is you'll start, and if you're an expert, you might put something in, and in the first graph visualization, you'll look at that, and you'll say, yeah, that looks about right. But what you can also do is expand the range of concepts you're looking at according to the individuals, the amount of time they've got, the level of knowledge they have, so you can see more or less concepts depending on your level of interest. So any user, if you've been studying something for 20 or 30 years, you can still find new things. And you can also use it to hypothesize. So if there's something that you're interested in, you can put in your first concept, and you can add in a second concept to see if it's related. So the key thing really is that the visualization is highly intuitive, and the machine has read 125 million items that nobody in this room, and even if we all got together, we couldn't read that much. And so it's found the inferences. So it's taking the connections and the ability to find those connections way beyond what an individual could ever do, doing a lot of the groundwork for you. So that's what I wanted to really cover, and I was going to hand back to Genevieve. Thank you.
Right, thank you very much, both. We do have time for some more questions. Shall we start? I think Bill had one from the first session. If we can start with Bill.
It strikes me that particularly when the goal of machine learning is a particular task, how to navigate this car through real streets, et cetera, and you're mentioning this enormous flood of data, it strikes me that you don't necessarily know what data is actually going to matter. So is the goal to just, in other words, does the machine end up picking out what the relevant things are in the process of the machine learning, or to what extent do you have to feed it the right information to optimize its learning?
Shall I start and then you can?
Yep.
Yeah. So it's a bit of both. You can't feed it completely irrelevant data. It won't work anything out about driving cars if you feed it data about cooking, obviously. But so you have to be feeding it relevant data, but then there is a process, and I think it is actually one of the hardest challenges of machine learning is to typically to get that data, the most appropriate data that really is going to train that and help that machine learn. So in the example of breast cancer, though, they didn't know what things were going to help the computer to understand, which bits of data were going to help the computer determine whether someone had breast cancer or not. And essentially, what it's doing is it's identifying the patterns in that data that's going to, that it thinks determines whether someone's got breast cancer or not. So you don't necessarily know from the start. So it's a little bit of an iterative process to work out what the data it is that you need. And there's a bit of a process of feed it some data, see what results you get, and then refine it. But I think part of the interesting bit about it for me is that there was a case where they were trying to test whether a computer was as good as a patent lawyer identifying which way a patent case would go. And they fed it data like, what's the weather? What the weather was like on the day, which court they were in, who the judge was. And it turned out that there was some of those factors were influencing the decision of the judge in the patent case. So that's what's partly what's interesting to me, is it'll actually start to help you understand what patterns it identifies as the thing that does determine the success of that task.
And once you get to that result, does the noise matter? In other words, do you need to tear out the things that turn out not to matter, or do they not matter? You can just leave them in there.
I would probably leave that to someone who has much. I don't know if you have a specific answer to that, but my experience is that you do at times have to be careful about the data you feed it, and you can feed it misleading data, and you have to be conscious of that. But the machine is, once you frame the task correctly, and you give it the results that you want it to achieve, then it is fairly good at identifying which things it cares about and which things are important. Although when you actually start to uncover and open it out and start to look at what are the things that have determined the success of that particular task, it can be quite surprising. I don't know if you have anything to add to that.
Yeah, I think there's definitely an element around the quality of the data and the misleading results, and there's also something related to volume. I think from our perspective, one of the things that was important to us was this interdisciplinary environment. So if you're an expert in your field, you know where to go to find really great information. But every day, new information is being created, and every day new websites are popping up. And there's a great quote from Michael Gazzaniga, the cognitive neuroscientist, that fantastic discovery in the future will come from interdisciplinary domains. So if you're a brilliant engineer and you go to a brilliant engineering database, you will probably find some brilliant engineering information, but you will not find anything else. So what we're specifically trying to help with is the fact that there is this huge amount of information, and clearly nobody will ever have time to analyse all of it. So if there is a connection, we'll find it for you. And I suppose the way in which we deal with some of the concerns you mentioned, like potentially noises, we only ingest high quality scholarly and academic information. So you don't have to worry about things like that.
Can I add one more bit to that? So to follow on from what you said, an example of that would be finding peer reviewers. If you just stuck with the authors in your domain, then you're going to get the authors from your domain. But there might be researchers in other domains who aren't necessarily in the same domain or doing the same science, but they followed exactly the same method. And there's actually you know, and then that's an open question then. Is a reviewer of a research article useful who's just carried out exactly the same method, but from a completely different domain? Potentially they are. And you wouldn't get that if you wrote a rule, a human wrote a rule about what makes a good reviewer. So there's an element of discovery, I think, which the computer could do without us.
This isn't really a question, it's a continuation of the answer.
Thank you. That's someone who knows.
So you're being very perceptive. Of course, if there was like one algorithm that could just learn anything, then we would all be out of work already, right? And all the money would already be piled entirely in California instead of most of it, right? But there are combinatorial issues to any of these problems as you're sort of hearing about these trade-offs, and every piece of software is written. And I've heard really big names, I'll say, like Andrew Ng, like lying, saying like, we don't program anymore. We do still program, it's just that part of the programming is being replaced by these methods. But there is architecture. Typically you're reducing, you're making modules, you're choosing which bits to allow to go together. It is still a thing to build a thing, but just like, you know, programming is changing just like publishing is changing, just like everything is changing. But it's not that there's one algorithm that just, you conceptualize it and then a system pops up in front of you. It doesn't happen.